Example 11.3. In this example, we'll study a hydrometer, which is a device used to measure the specific gravity of a fluid. Hydrometer is simply a small cylindrical glass tube with lead weight, which is placed into a fluid. Part of it is going to sink and part of it is going to be exposed in the air. The top part of the hydrometer extends above the liquid surface, and the divisions allow you to read the specific gravity directly. A general hydrometer is calibrated in such a way that in pure water, it reads exactly 1 at the air-water interface. The first goal of the problem is to obtain a relationship for the specific gravity of the fluid as a function of delta Z, which is the mark corresponding when you read the hydrometer. Part B is to determine the mass of the lead that must be poured into a 1 centimeter diameter and 20 centimeter long hydrometer, which flows halfway in pure water. To analyze this problem, we're going to neglect the weight of the glass, and also we're going to disregard the curvature at the bottom of the glass. Notice that in the hydrometer we have two forces, the buoyancy force and the weight, and we don't have any other one. Therefore, we could say that the buoyancy force is equal to the weight. If we do this analysis for water, pure water, in which the value that we're going to, the elevation that we're going to have is going to be Z0, then we said that the buoyancy force is going to be density of water, G, and the volume that is submerged. For pure water, the volume that is submerged is going to be simply the cross-sectional area of the glass times the value of Z0. Therefore, the buoyancy force for water is going to be density of water, G, A, and Z0. If we do this analysis for any other fluid, so let's just do fluid, we could say that the buoyancy force for that other fluid is going to be the density of the fluid times G times the volume that is submerged. For any other fluid, the depth is not going to be ZO anymore, but it's going to be simply an addition of C naught plus a delta C. Notice that the weight of the hydrometer does not change. So if we apply this force, this relationship, the buoyancy force means that the buoyancy force that is applied for the water is exactly the same buoyancy force that is applied for the fluid, since the weight of the hydrometer does not change. Therefore, we could make them equal to each other, and we write density of water, G, A, Z0 is equal to density of the fluid, G, and the volume submerged for the fluid is going to be equal to A, Z0 plus delta Z. The value of G cancels, is the same tube, so the cross-sectional area cancels. And then we simply have Z0 is going to be Z0 plus delta Z, and is going to be the density of the fluid divided by the density of the water. Now notice that this relationship is the same thing as the specific gravity of the fluid. So if you're able to have a reading for delta Z, you should be able to find out the specific gravity for that particular fluid. Notice that the value of delta Z is going to be positive if the fluid is lighter than pure water, but if it's denser, it's going to be negative. Let's now do part B of the problem. We need to calculate the mass of the lead, and we're going to use the relationship that the buoyancy force is equal to the weight. The only weight acting at this moment is going to be for the lead, since we're neglecting the weight of the glass tube. So we could say that the weight of the lead is going to be equal to the buoyancy force. The weight of the lead is simply the mass of the lead times gravity, and the buoyancy force is going to be simply B, the density of water times G times the volume in which it is submerged. For this particular case, the weight that is going to be submerged is going to be equal to the cross-sectional area times Z0, since we're doing it in pure water. In this relationship, notice that the value of G cancels in both sides. So we're substituting this value over here, and we find that the mass of the lead is equal to the density of the water times the area times Z0. Now notice that we have that the density of water is equal to 1,000 kilograms per meter cubed, and we have that the value of A for the area is going to be pi times the value of the radius, which is equal to 0.005 meters to the second power, and the value of Z0 is equal to 0.1 meters. If we multiply this out, we find that the mass of the lead is going to be equal to 0.00785 kilograms. Please make sure to go back and be able to calculate all these values and understand the purpose of a hydrometer.